Okay, so the next section here is 31.7. This is resistor circuits. So in this section, we shall combine what we learned with parallel and series resistors to learn how to handle those complicated circuits. So let's look at a circuit which combines parallel and series resistors. So let's analyze the circuit below. So we have our battery again, and then we put a resistor here. Let's put one here which is in parallel. So let's call this R1. Let's say this is R2, R3, this is R4, R5, R6, R7. I'll just put E there. So we can analyze this circuit with the rules that we've learned from parallel and series circuits. Okay. So to start off first, let's look at the parallel circuits and break them down into series circuits. So what I would say is always start with the parallel circuits first, unless it's clearly obvious on a series circuit. You always start with the parallel circuits. Okay, so we'll do that next. So the parallel circuits are the one that has R2 and R3, and then there is one with R4 and R5. So let's do those two first. So let's say that R equivalent is equal to R2, R3 over R2 plus R3, and then we shall do R equivalent prime is equal to R4, R5 over R4 plus R5. And later on, I'll give you numbers that we can put in. Okay, so let's break it all down first. So once we've broken those parallel circuits down, let's redraw the circuit. So we shall redraw it this way. So we have one there like that. And then I'll go down this line and put R equivalent here. So this was R1, and this is R7. And then we have here another R equivalent prime. And then we have R6, I believe. Let's see. Yeah, that's R6. And then it goes like that. So this is what we have now with that circuit, as you can see. So now we can take R equivalent prime and R6. Those are in series. Notice that this pin here is not a junction. Okay, I'm only drawing it for convenience. Okay, so let's now do the next one, which is a series circuit. Is R equivalent prime and R6. Okay, so let's do that next. So R equivalent double prime is equal to R equivalent prime plus R6. So we'll redraw the circuit after that. The new circuit is going to be this. That is R1 again. And then we have going down this line, R equivalent. And then we have here now R equivalent double prime. And then we have R7. So that's E. So this is where we are now. So next, what do you see there? You see a parallel circuit. Which of this is parallel?
R1 and R7.
Which one?
R1 and R7?
No, they are not parallel because there's an R equivalent between them. So this branch in the middle here means that they are not parallel.
REQ and R double prime are the
Yes, those two are parallel. So let's deal with those next. So the next R equivalent, let's say triple prime is equal to R equivalent double prime divided by R equivalent plus R equivalent double prime. Okay, so now we've broken down that parallel circuit into a series circuit. So let's redraw the circuit.
Can you scroll back up for a second?
Yes. All right. So now I'll redraw the circuit. So we'll see that this is what it looks like now. We have our R1. We have now R equivalent triple prime. And then we have R7. Now you can see they are all now in series with each other. So this can be now broken up into a circuit that looks like this. So this is now R equivalent 4, where R equivalent 4 is just equal to R1 plus R equivalent 3 plus R7. Okay, so now we've broken that circuit up into a simple equivalent circuit, which is a simple circuit. Now we can find the current through the circuit by just taking I. So this is your current I. So the current through this equivalent circuit is just given by the battery EMF divided by R equivalent 4. We will use this later on once we learn how to do this. Okay. Any questions on that? Okay, let me give you one to try and then we'll go from there. So let's find the equivalent circuit for the arrangement below. So take this like that. So this is R1, R2, R3, and R4, where R1 is equal to 10, R2 is equal to 5, R3 is equal to 15, and let's say R4 is equal to 10. So let's see what you get for the equivalent resistance of this arrangement here. Let me rewrite this nicely. And I'll say that the battery EMF, let's say, is 1.5 volts. Okay, so let's get some of the answers now. So we can break this down the following way. Actually, before we do that, just give me your equivalent resistance for the entire circuit.
For the final,
Yes.
I've got 9.33 ohms.
Okay. Is that what everybody's getting? Okay, good. So let's break it down this way. So we see that one of these is going to be an equivalent resistor, and then we're going to have another equivalent resistance here, and then it goes that way. So the first one, R equivalent, we can say is R1, R2 over R1 plus R2, and the second one, R equivalent prime, is going to be R3, R4 divided by R3 plus R4. Okay, so once you look at it that way, it becomes straightforward. So then, the first R equivalent, what does that give you?
3.33.
Okay, 3.33, thank you. And the R equivalent prime, 6.0 ohms. So now we can combine the two to get a final equivalent resistance. I'll call it R equivalent double prime. This is just going to be R equivalent plus R equivalent prime. This is going to be 3.3 plus 6, so 9.3. Let's do it this way. So it's 3.33 plus 6, so 9.33 ohms. So that's your equivalent resistance, and we have 1.5 volts here. Okay. So now, did everybody get that? Okay, so now that we have that, the next thing is to find the current through each element in the circuit and to find a potential drop across each element. Okay, so let's work our way through that. So we're going to work our way backwards. First of all, let's find the current I in the circuit. So I is going to be equal to the EMF divided by the equivalent resistance double prime. So it's going to be 1.5 volts divided by 9.33 ohms. So what does that give us for current in the circuit?
0.1.
What?
0.1607.
0.1607 amperes. Let's keep the decimal point so that it comes out pretty well as we check it when we are going along. So we have that current going through the circuit. So now the next thing we need to do is to draw the equivalent circuit backwards. So we have this and that. So this is 1.5 volts. We know the current through the circuit is 0.1607 amperes now, going this way. So this was R equivalent and the R equivalent prime. That same current goes through each of those resistors. Therefore, we can find a potential drop across R equivalent and R equivalent prime. So we can say that since I and I meaning 6.160. So since that goes through R equivalent and R equivalent prime, we can find their potential drops, or we can find the potential drops. So the potential drop across R equivalent is just equal to current times R equivalent, which will be 0.1607 amps times R equivalent. What was R equivalent? 3.3. So what does that give us for potential drop? So
When is
hold on a second.
6.33 and 9.33?
That is the whole thing. We've already used that part. So this was, what did you call this? What did you say it was? Okay, let me write it below there. Actually, let me rewrite this so that I can, because I want to set it up so that we can add them all up. So the potential drop across R equivalent is equal to I R equivalent, which is 0.1607 times 3.33. So you said this is equal to 0.1, and then the potential drop across R equivalent prime is going to be equal to the current times R equivalent prime, which is 0.1607 times 6. What does that give us? 9642 volts. So add those two and see what you get. Okay, so this is pretty close to 1.5, which is what we expect. So at every point along the line, we should be able to get 1.5 volts. Okay, so the potential drop, you see that R equivalent and R equivalent prime are not the same. So the potential drop across each one is going to be different. One of them is almost twice the other, so there's a difference in potential drop, which is about 0.96 and 0.53. Okay. Questions on that? Okay, so let's go backwards to the next level. So now we're going to redraw this again. So going back, we go to this one here. So the R equivalent was a circuit here that had this, and then the other one was this one here. So now this is R1, R2, R3, and R4, I think. Let's make sure. Yes. So we now have the potential drop across R equivalent, which was 0.5305. Since R1 and R2 are in parallel, it means that they each have the same potential drop. So the potential drop across R1 is equal to 0.5305, and that will be the same as the potential drop across R2. Okay. And since R3 and R4 are in parallel, they have the same potential drop, so that will be the potential drop across R3 is equal to the potential drop across R4, which is equal to which is the 0.96. Let me rewrite this here. I'm running out of room here. The potential drop across R4 is equal to potential drop across R3, which is 0.9642 volts. The reason we have it, the reason I'm doing it that way is now what we shall do is, since we have a current going through here, this current is 0.1607 amperes. That current goes through here, it splits up and then continues splitting up here. So we can say that since they each have the same potential drop, then the current I through I1 is equal to the potential drop across R1 divided by R1, and the current through R2 is equal to the potential drop across R2 divided by R2. Okay, so I1 is equal to what? So I1 is 0.5305 volts divided by R1. What is R1? So this is equal to 0.05305 amperes. And then the current through I2, the current I2 is equal to delta V R through R2, which is 0.5305 volts divided by R2. What was R2? 5 ohms. So that doubles it. So what would that be? Okay. So the key then is to add I1 and I2. So I should be equal to I1 plus I2, which is equal to 0.05305 plus 0.1061 amps. So what is the sum of those two? Which is close to 0.16. We want it to be close to 0.16. Okay, so it depends upon the way you've rounded it up. So those two, see the current 0.1607 is I, so I is equal to 0.1607, and that should be equal to that. Okay, so that means we've rounded it up a certain way. So give me more decimal points, and let's see what we have. 0.5305. If there is more behind, I think that will help. But you can see the point is that the current I should be equal to I1 plus I2. It's not exactly equal now. We have 0.160. If you want to leave out some of the decimals, we can say it's 0.161, and that should equal to 0.16. So it's pretty close. It's off by 1,000, but it's pretty close. Let's continue along that same line so we can find a current that goes through R3 and a current that goes through R4. The current going through R3 using the same approach, I3 should be equal to the potential drop across R3 divided by R3, and the current going through R4, which is I4, is a potential drop across R4 divided by R4. So what is I3? Remember that since R3 and R4 are in parallel, they have the same potential drop, which is 0.9642. So this is 0.9642 volts divided by R3. What is R3? 15. What does that give us? And then what is R4? 10 ohm. 10. Okay, so it's get 0.09642 amps. So add it together and let's see what you get. So I should be equal to 0.1607 amps, and that should be equal to, what is it? Yes, what is I3 plus I4?
0.1607.
Okay, so this one is exact. So you can see that the current splits up between R1 and R2, then rejoins at that branch there and goes and splits up at R3 and R4 and rejoins again and comes back. So the total current going to the circuit should be the same. Okay, so we found the current through each element. We found the potential drop across R1 and R2, R3 and R4, and the current through R1 and R2 and R3 and R4. So that's how you do it. So there are quite a lot of circuits we can do that way, but this is the general approach. So you break it down and get equivalent resistance and break it into a single circuit and get a current, and then you work your way backwards and then get the current through each element, potential drop across each element until you've reconstructed the circuit. Okay. Any questions on that? And as you're going along, you can be checking it to see if it matches. So the potential drop across the elements should always match up to be equal to the potential drop across the battery, and the current through all the elements should all add up. So if you come to a junction, the sum of currents going to the junction should be equal to sum of currents leaving the junction.